In this video, we're going to look at another transcendental function called the logarithmic function. Now, one thing you need to understand is that the exponential function is a one-to-one function. So that means it's going to have an inverse. And the inverse of an exponential function is this function that we're going to call the logarithmic function. So this function here, f of x equals log base b of x, and that's how you read this thing right here, log base b of x. Okay, this is going to be the inverse of b to the x, my exponential function. Now the values here are going to be very similar to the values of the exponential in terms of the base. The base here for this logarithm is the same base here for this exponential. So b still has to be greater than 0, and b is not going to be equal to 1. Now x, however, which is the value we're going to use for our domain of the function, has to be greater than 0. And there's a reason for that, and it has a lot to do with the fact that this is the inverse function. But we'll talk about that in a second. So if log base b of x is the inverse of b to the x, well, conversely, you can say the same thing, that the logarithmic function is the inverse of the exponential, and the exponential is the inverse of the logarithm. So essentially what you have is this statement right here. And what it says is that y equals log base b of x if and only if x equals b to the y, which shows you the relationship between exponentials and logarithms. And this is a two-way street here, in that if I have this, I can assume this is true, and vice versa. If I have this, I can assume this is true. These two statements are equivalent statements. Now, think about how inverses work. Inverses take you from one function to from one set to another set through some function. That's how functions work. And then inverses work the opposite way, right? The inverse will take you the opposite way. If you're fuzzy on inverses, then I'll have to post a video that reviews inverses, and I'll do that on the lecture site. So if this is how inverses work, then what we're basically saying is that one function, y equals b to the x, goes this way, and the other function, y equals log base b of x, goes the opposite way. Alright, well, to kind of think about how this is going to work, let's not just do a general exponential log, let's do a specific one. So let's go with y equals 2 to the x. And then the inverse would be y equals log base 2 of x, because the base has to be the same. Base here is 2, base here is 2. So let's think about this. If I plug in 0 into this function here, what's going to happen? I'm going to get 1. If I plug in 1 into that function, I'm going to get 2. If I plug in 2, I'm going to get 4. I plug in 3, I'm going to get 8, etc. Now, if I look at the inverse function, if I plug any of these values into the inverse function, it should get me back to 3. So the log base 2 of 1 is 0. The log base 2 of 2 is 1. Essentially, I'm saying I'm plugging in 1, which is here, and that's going back to 0. I'm plugging in 2, which is here, and that's going back to 1, etc. Log base 2 of 4 is 2. Log base 2 of 8 is 3. And what you're really looking at here with these logarithms is, this is my base, this is the exponent, and this is the answer I got. So when we're looking at a logarithm, we're going back to the exponent. We have the answer, we're going back to the exponent because it came from this. Now think about this. The domain for the first function is here, the range for the first function is here. So this is domain, this is range. This is where we start, this is where we end. This is the domain for the logarithm, and this is the range for the logarithm. They're the reverse. Well, what was the domain for the exponentials? For all exponentials, my domain was negative infinity to positive infinity. And my range was only positive values. Well, guess what? The domain for the logarithms are going to be only positive values, and the range is going to be negative infinity to positive infinity. And that's why we have this. X, which is my domain, can only be positive, because the only answers I'll get out of an exponential, which is the range for the exponential, is positive, and that's now the domain. So the idea of inverses is very important with learning how logarithms work. So now that you know where the logarithm comes from, it comes from the inverse of an exponential, we have to then think about how we work with logarithms. And we've already kind of talked about that. So here's a couple examples. Evaluate each of these following logarithms. So let's look at the first one, log base 2 of 32. So when I'm doing this log base 2 of 32, I'm trying to figure out, alright, what the answer is. Well, essentially this is saying 2 to some power equals 32. So that's the way I'm going to answer this question, is think about 2 to what power gives me 32, and I'm going back to find the exponent. Well, that would be the 5th power. So here's my base. Here's the answer I would get. I'm trying to figure out what exponent gives me that answer. Okay, let's do another one. Log base 3 of 1. Well, 3 to what power gives me 1? Well, anything to the 0 power gives me 1, so log base 3 of 1 is 0. How about log base 4 of 2? Again, I'm trying to figure out what this is. What exponent is this? 4 to what power gives me 2? Now I'm getting smaller. Usually with exponents you would get bigger. However, roots can be exponents, and roots would make you smaller. Well, the second root of 4 gives me 2. Second root is the same thing as the 1/2 power. So that's the power that would give me 2. So that's the answer for the logarithm. Log base 10 of 1 over 100. So I got to say, alright, well, 10 to what power gives me 1 over 100? I'm trying to figure out that power. Well, we know that 10 to the second power gives me 100, but I need to do 1 over 100. Well, if I do 10 to the negative second power, that's 1 over 10 squared, which is 1 over 100. So that exponent had to be negative 2. Now, one thing that happens with these logarithms is base 10 logarithms you will see written this way: log of 1 over 100. They'll drop the base off. Normally we'd write the base on all of these, but for base 10s we call this a common logarithm. They'll drop that base off and you'll see log of something. If you don't see a base written here, there's a little subscript that should be there. If we don't see that base there, assume it's base 10. Your calculator has this button on it. That button is a log button. That button is a base 10 logarithm. So if I want to do this logarithm or this logarithm or this logarithm, I can't do it with my log button on my calculator necessarily, because the log button on the calculator is base 10. Now there is a way to do it, but I can't just do it by hitting the log button. So this is something we're going to have to talk about later on, of how we use this button on our calculator to do other logs. But right now you don't need a calculator to do these logarithms. If I give you any one of these logarithms, you should be able to do them without a calculator, because you just need to know what your exponents were, and these are easy exponents. Now some are not going to be so easy, and we're not really going to look at these right now, but some would be something like this. Log base 3 of 10. Like if I asked you to do this and figure out what the answer is, well, you got to say 3 to what power gives me 10. Well, that's not easy because it's not a whole number power. If this was a 9, that would be easy. It would be 3 to the second power gives me 9. But 3 to what power gives me 10 is not very easy to do. Now what you could do is you could say that the answer is roughly 2.1, right? You know it's going to be a little bigger than 2 because 3 to the second is 9, so 3 to the 2.1 should give me 10, but that's just an estimate. There's going to be a way to find out a better answer and to be able to use your calculator to find an answer to this, but we can't just simply hit this button and then somehow get the answer. So we'll talk about that as we move on. Right now, the logarithms you'll look at are going to be fairly easy logarithms to work with, okay? Where the answer is a whole number answer or even a fractional answer that deals with a root, negative answers, but something that's not some infinite decimal like what this actually is going to be, because this is some infinite decimal that just keeps going and never repeats. Okay, so now that we know how to work with a logarithm and just basically in terms of evaluating a logarithm and where a logarithm comes from, the next thing we're going to talk about is graphing a logarithmic function. This idea also comes from the relationship with inverse functions. Inverse functions graphs are symmetric to one another with respect, Inverse functions graphs are symmetric to one another with respect to the y equals x line. The y equals x line is this line right here. This is what we call the identity line. It's essentially the 45-degree line that cuts the x and the y-axis in half. The graphs of any inverse functions will be symmetric with respect to that line. So if we want to start to look at what a logarithm graph looks like, let's look at a specific example. Let's look at f of x equals 2 to the x versus g of x equals log base 2 of x, and you'll see the relationship between their graphs. So 2 to the x, we know that 2 to the x looks like this. Goes through this point, 0, 1, has this increasing shape because the base is bigger than 1, and there you go. Now if I flip that graph along the y equals x line and creating a symmetric picture, what I'm going to get is this picture. Something like this. And it's going to go through this point, 1, 0. And that's going to happen. Essentially, any point AB that's on one function, the point BA is on the inverse. This would be on f of x. This would be on f inverse of x. We take all our points because the domain and range is flipped around. The x's and y's are all flipped around. So 0, 1 is on one function, 1, 0 is on the other function. That goes for all points. So this right here is the graph of y equals log base 2 of x. This here is the graph of y equals 2 to the x. They're symmetric with respect to the y equals x line, and this gives you an idea of what a logarithmic graph looks like. It has this increasing shape. What happens is instead of having a horizontal asymptote like the exponential does, we get a vertical asymptote. Now remember, there were two different exponential graphs. There's the increasing exponential graph, which we just looked at here, and therefore you have this increasing logarithmic graph. But there was another exponential graph that you could have looked at as well. So let's take a look at that one. So let's look at this one. How about y equals 1/2 to the x versus y equals log base 1/2 to the x of x. So if I draw the first one, this exponential function, the graph looks like this. Goes through this point, 0, 1, has this decreasing shape because of the base. And if I flip that along the y equals x line, what happens is I get this picture. It goes through this point 1, 0. And this would be the graph of my logarithm with a base smaller than 1. This is log base 1/2 of x. That's my function there, as opposed to this one is my y equals 1/2 to the x. So we're looking at these two functions, and there are two exponential graphs. Therefore, there's two logarithmic graphs based off of those exponentials. So looking at this, if we have log base b of x, we have these two graphs again. One graph looks like this for my logarithms. That's for y equals log base b of x, where b is between 0 and 1. Okay. And then we also, this one, and this one is for y equals log base b of x, where b is bigger than 1. They both go through this point 1, 0. And that comes from the point 0, 1 on the exponential. But there are two different logarithmic graphs, just like there's two different exponential graphs. So the domain for both of these is 0 to infinity. If you look, these graphs are only existing on the positive x-axis. Okay. We don't have any graph over here. These x values and also the y-axis, which would be an x value of 0, do not have points on our graph. So it's strictly positive values are in our domain. However, our range goes from negative infinity to positive infinity. Both of these graphs go from the top of the y-axis down to the bottom of the y-axis. Range are your y values. They both have an x-intercept at 1, 0. They both have a vertical asymptote, that is the y-axis, depending on which logarithm you're looking at. Remember, these are two different graphs. I put them on top of one another, but one is the graph for a base bigger than 1, and the other one would be for a base between 0 and 1. If we have a base bigger than 1, we have the increasing graph, that's the red one. If we have a base between 0 and 1, we have this decreasing graph, that's the blue one. Both functions are continuous as long as we stick to the domain. They're all one solid piece as long as we stick to the domain of positive values only. This is important. The domain for logarithms is only positive values, which means when I'm looking at log base b of x, the only thing I can take the logarithm of is a positive value. Okay? I cannot take the logarithm of 0, and I cannot take the logarithm of a negative. The only values I can take any logarithm of, regardless of the base, and remember that base has to be positive and not equal to 1, because that's the base from the exponential, but regardless of the bases that fit that criteria, I can only take the logarithm of a positive value. So let's sketch a couple of logarithmic graphs. And I'm going to put them all on top of one another so you see how it changes. If you know how to do translations, then you should be able to draw every one of these graphs. And that's the only way we're going to do it. Much like exponentials, we're going to graph these using translations. First, let's graph this log base 10 of x. The key here is looking at the base. The base is 10. A base 10 logarithm is a base bigger than 1. That logarithm should look like this. It should go through this point 1, 0. So this would be y equals log base 10 of x. Now remember, when it's base 10, I don't have to write that base. So you might see it as log x. Same thing for all these. I don't necessarily have to write the 10. You can, it's not wrong, but I don't have to write the 10 on either of them. And it's assumed that there is a base 10 there. I just wrote it so that you clearly see what the base is and that the base is bigger than 1. Okay, so let's go to the next one. Here's our next one. Log base 10 of x plus 2. Now I'm adding 2 inside my logarithm. These parentheses are important. The parentheses mean it's happening inside the logarithm. This is different than this. This I'm not adding 2 inside the logarithm. This is adding 2 to the whole function. Here, having these parentheses here makes a difference. The 2 is added inside the logarithm. So the idea is if I ever add 2 inside my function, I should move it to the left 2 units. So this is going to be moved to the left 2 units. So this point here is going to go 1, 2. It's now going to be there. That point would be negative 1, 0. The vertical asymptote that was the y-axis here is also moved to the left 2 units, which puts it at negative 2. If I then draw the graph based off of that, I would get this picture. This would be y equals log of x plus 2. Now if I want to additionally take this logarithm, go to the next step here. Log base 10 of x plus 2 minus 1. Well, plus 2, move it to the left, we already did, and then this one additionally moves it down. This minus 1 will move it down 1 unit. So if this comes down 1 unit, this point would then be here. Let me change this color up a second. And I'm going to get this point, which would be negative 1, negative 1. And my graph should go through that one. It should look something like that. The vertical asymptote slides down 1 unit, but basically it's sliding down along itself, so it's still in the same location. So here's the 3 different graphs, how they all relate to one another, because they all have the same base. However, they're moved in different directions. When it comes to these, there's really 3 things I'd be looking for here, just like the exponentials. The 3 things I'd be looking for in these graphs are, do you have the right shape down, because the base can change the shape a little bit from increasing to decreasing. Did you move this point to the right location, here, here, to find out the location of the graph as a whole? And did you move the vertical asymptote, if it needed to be moved, to the right location? So do we have the right shape? Do we have the point in the right location? And do we have the vertical asymptote in the right location? If you have these 3 things, you have a pretty decent logarithmic graph. Now it's not going to be perfect, but it's good enough really for what you need it for. So that's what I'm looking for with these logarithmic graphs. Just like the exponentials, I was looking for largely the same 3 things. The difference was exponentials had a horizontal asymptote instead of a vertical asymptote. The next thing we're going to look at is the natural logarithmic function. And this is just another log, just like any other log, but it has a very specific base, and we're using that natural number e as the base. So a log function with base e is called this natural logarithmic function, and we denote it a slightly different way. We could write it as log base e of x, because that's what it is. It's a logarithm base e, but we actually don't write it that way because this is a fairly common logarithm. We're gonna, just like we take the base 10 logarithms and don't write the 10, we're gonna take these logarithms and we're gonna change the format, and we're gonna write it like this. We're gonna write it with this lnx, and that's the natural log of x. Okay? And you got to see this logarithm really as a logarithm that looks like this, a logarithm base e. So all the same things that we just got done talking about with logarithms are the same for this logarithm. It just has a specific base. And this logarithm, natural log of x, is the inverse of this exponential, e to the x. Well, this is a logarithm base e. E is roughly 2.7. So the base for this logarithm is bigger than 1. So the graph of this logarithm is going to look like every other logarithm base bigger than 1. It's going to still go through this point 0, 1. It's going to have this increasing shape. This will be y equals the natural log of x graph. So if I wanted to graph this, I can do it the same way as I did the other ones. Domain, same deal. The domain is greater than 0. Again, this is a logarithm like all logarithms. It just has base e. So the domain still has to be positive values only. I can only take the log of a positive value. So if I ask you one of these two questions and I say find the domain for each of these and graph them. Well, if you think about just the domain first, we'll graph them in a second, but think about the domain. The domain is that this thing inside here has to be positive, so x minus 2 has to be greater than 0, which tells me that x has to be greater than 2. This is my domain. If x is bigger than 2, I'll always take the log of a positive value. Same deal with this one. This one, the domain is such that this thing has to be greater than 0, which tells me 2 has to be greater than x, which is the same thing as x is less than 2. That's my domain. So these two functions basically have opposite domains. So if we think about what their graphs should look like, well, that should have something to do with their graphs. This one's defined only in terms of x is bigger than 2. This one's defined for x is smaller than 2. So let's think about what these two graphs will look like. So let's do the first one. Let me erase this here. So if I draw this first one, let me change my color up. Alright, if I'm going to draw this first logarithm, y equals natural log of x minus 2. I should take my basic logarithm, which looks like this. I shouldn't have erased the last one. And if I have a minus 2 inside the logarithm, I should move it 2 units to the right. So now it's going to be here. This point, which was 1, 0, is now going to be 3, 0. My vertical asymptote is going to be right here at 2, because it was the y-axis and it shifted 2 units over. So that's what that logarithm is going to look like. Now if I look at my other logarithm, well, let's look at this one. Y equals the natural log of 2 minus x, which is the same thing as the natural log of negative x plus 2. Now there's a problem here, and this is a problem I've discussed before that you should have seen when you first started doing translations in algebra. And the idea is when you have a negative inside your function, you need to think about the way you look at this and write it this way. The natural log of negative x minus 2. In that the entire inside of the function has to be multiplied by a negative and not just the x. This way, the negative inside the function tells you need to flip over the y-axis. And then this is telling me a minus 2 means move to the right. Just like minus 2 over here said move to the right. So if I take my original graph, let's erase some of this. If I take my original graph of a logarithm, which is here, and what I'm going to do is flip it over the y-axis, which is going to put me here. And this point's going to be negative 1, 0. And then shift it to the right 2 units. It's going to put my vertical asymptote at 2. And it's going to make my graph, let me change the color here. Let's go with this. It's going to put my graph to look like that, because this point's going to move 2 units this way, which puts me right here. So that blue graph is the graph of this function. Look at the domain. X is less than 2. Here's 2, and all the values I'm using are less than 2. So that's the graph of that one. But graphing these logarithms is the same as graphing any logarithm. Next, we got to start discussing some properties of logarithms. Some of these properties are just the properties based off of the definition of how a logarithm works, and that's really in terms of the exponential, and others are properties based off the fact that this is an inverse function for an exponential function, and these are just properties of inverses themselves. So let's look at the first one, and I gave you 2 tables here to look at. One for logarithmics in general, and one specifically for natural logs. Now they're the same exact properties. The only thing is that natural logs, we write the notation a little differently with the ln. So it might look different, but it's really the same. That's why I put them side by side. So first, log base b of 1 equals 0. So log base anything b of 1 should always give you 0. Why? Because b to the 0 equals 1, because of the way the exponential works. So if I do natural log of 1, I should get 0. That's just a log base b, like base e. And I should get 0. Again, because e to the 0 equals 1. Log base b of b. If the base and the thing I'm taking the log of are the same, I should just get 1. Why? Because b to the first equals b. Same thing goes for natural logs. The natural log of e equals 1. Why? Because e to the first equals e. So those are just two properties based off of how a log and an exponential work. The next two properties are dealing with inverse properties. This property here is called the inverse property. This property here is called the one-to-one property. So the inverse property, something you should have learned about inverses, and that was if I take a function and I do its composition with an inverse of that function, they should just give me x. Well, these two functions are not general functions right now. One's the log and one's the exponential, or vice versa. So if I take an exponential, which is here, and I plug it into a logarithm, so I'm taking the log of an exponential, that's the composition of two functions that are the inverse, and I should just get x. And what we think of here really is that this and this kind of cancel, and I just get the x out of it. Same thing here. I'm taking a log and I'm plugging it into an exponential. So I'm doing the composition of two inverse functions. We think like these two should really cancel each other out, and I should just get x. Natural logs work the same way. Natural log and e are the inverse, I get x. E, natural log are inverses, I just get x. We'll deal with this more later when we discuss solving equations with logs and exponentials in them, and that's a big property in doing that. But right now it's just getting used to kind of how it looks. This next one's called the one-to-one property. These are one-to-one functions. Logs and exponentials are one-to-one. So what that means is that if I have two logs that are equal to one another, the bases are the same, well then the things inside the logs also have to be equal to one another if it's a one-to-one function. Same thing here. If I have two logs that are equal and the bases are the same, being that they're both natural logs, the thing inside the logs have to be equal. So just to see how some of these properties work, here's a couple of examples that you could simplify. Log base 5 of 5 to the x. Well, 5 to the x is the inverse of log base 5, and I'm plugging this into a logarithm. So in a way we think of these two things like they cancel, and we just get x. Here's 6 to the log base 6 of 20. Log base 6 is the inverse of 6 to a power. So in a way we think of these canceling, and I'll just get 20. It's not x, it's a 20 this time, but that's it. They'll cancel and I get the 20. E to the ln of 5. Ln, natural log, is the inverse of e to a power. Cancel, I'll just get 5. At 2 ln of e, this is e to the first. Well, ln and e are the inverse, and the ln of e should cancel. I should just get 1, so this gives me 2 times 1, which is 2. Now the bases have to be the same for this to work out. If I gave you 6 to the log base 5 of 20, I'm not going to get 20 because I can't cancel these two things. The bases aren't the same. But if this was a 6 here, now they're the inverse of one another. Now they can cancel and just get the 20. In this case, it will be equal. So that's important. All right, a couple more properties when it comes to logarithms. These properties are known as the expansion properties. Okay, these properties work with any base as long as the base fits the criteria for bases for logarithms, and that has to be a positive real number, right? The base has to be a positive real number, not equal to 1. We're going to let n in these formulas be any real number, and u and v be positive real numbers so that our logs are defined. So here's the deal. Look at this first one. I give you the same thing as I did in the last one. I give you this table has two sides to it. One's regular logs, the other side's natural logs. They're the same properties. This property and this property are the same, just in terms of the two different formats of writing logs. But let's look at this first property. I have log base b of a product, u times v. So if I am taking the log of u times v, the log of a product, I can take that product and split it apart. How? I can split it apart by using two separate logarithms. I could take log base b of u plus log base b of v. I can write one logarithm as the sum of two logarithms. That's taking a product inside a logarithm and splitting it apart as the product of the sum of two logarithms. Okay? So the log of a product is equal to the sum of logs. That works the same way with this log. This is natural log. A product inside the logarithm turns into the sum of logarithms. And it's natural log of u plus the natural log of v. Okay, let's go to the next one. Here I have a division inside my logarithm. So if I'm taking the log of division, and this is inside the logarithm, that can turn into the subtraction of logarithms. And I do the log of u minus the log of v. Same thing goes with natural logs. And the last property, which might look a little nicer if I wrote it like this with these parentheses here, in that I'm taking let's do it like this maybe. If I'm taking the log of something to a power, now that something to a power is inside the logarithm. If I'm taking the log of something to a power, what I can do is take that power and pull it out to the front of the logarithm as a multiple. So this is now a multiple n times a logarithm. Same thing goes here with natural logs. So there are three properties. The key to all of these properties are the operation is inside the logarithm first. Products inside the logarithm turn into sums. Divisions inside the logarithm turn into subtraction. And a power inside the logarithm comes out front as a multiple. So these properties are typically called the expansion properties. And these are coming from my exponent properties, really. There's a way to prove every one of these using just your general exponent rules. So to start getting some practice with these, we look at this. Expand the logarithm expression, natural log of 6, in terms of only natural log of 2 and natural log of 3. So what are we going to do? We're going to say, okay, natural log of 6 is equal to the natural log of 2 times 3. Well, that's a product inside the logarithm, so I can write that as natural log of 2 plus the natural log of 3. And now I wrote natural log of 6 in terms of natural log of 2 and natural log of 3. How about natural log of 2 over 27? Well, I could write this as the natural log of 2 over 3 to the third. So I could write this as the natural log of 2 minus the natural log of 3 to the third, because division can turn into subtraction. I can write this as natural log of 2 minus 3 natural log of 3, because this power can come out to the front as a multiple. So then my final answer here is this equals this, and I wrote it in terms of natural log of 2 and natural log of 3. Now those were two easier examples. This is more likely what you're going to see when it comes to problems. It's going to say expand the logarithm and you're going to be given a certain logarithm like this. So if I'm going to expand these, I got to say products go to sums, divisions go to subtraction, and powers come out in front as multiples. So I'm going to rewrite this logarithm. Log base 4 of 5x cubed y equals, well, the log base 4 of 5 plus log base 4 of x cubed plus log base 4 of y. These things in here are all multiplied together, which means that they should all be added together with logarithms. The base the whole time stays the same. You cannot change the base right now or just drop the base. It's the same the whole time. The only other thing we can do is with this one, that power can come out. So I'd write this as log base 4 of 5 plus 3 log base 4 of x plus log base 4 of y. Okay? And that would be the expansion. If you look at b, b was the natural log of the square root of 3x minus 5 over 7xy squared. So first thing I'm going to do is I'm going to take this division and turn it into subtraction. So I have the natural log of the square root of 3x minus 5, which we're going to write as a 1/2 power, minus the natural log of 7xy squared. Now I want to keep expanding. This power is going to come out as 1/2 natural log of 3x minus 5 minus, this is a product just like the previous one, and I'm going to write that as a sum. But the thing is, this whole logarithm is being subtracted. So whatever I expand this to, it still has to be subtracted. So I'm going to put parentheses, natural log of 7 plus natural log of x plus natural log of y squared. If I don't put those parentheses and I wrote, say, this, that would be wrong, because you're only subtracting the 7 when really all of this was in the denominator. So I have to put the parentheses around it to remember it's all being subtracted. Even though expands is addition in itself, it was in the denominator and now it's being subtracted. So then I'll write this as 1/2 the natural log of 3x minus 5. I'm going to distribute this negative in, so I'm going to get minus the natural log of 7 minus the natural log of x minus 2 natural log of y. I'm going to pull that power out, and this would be the full expansion. I cannot do anything more here. 3x minus 5 is subtraction inside a logarithm. There's no rule that says we can do anything with subtraction. So that stays. This is the full expansion. What you ideally would like to do eventually, when you get some practice with this, is to be able to jump from here to here. Right now, I would say do these intermediate steps because you need practice doing it. But when you get to calc, you're going to kind of be expected to know how to just jump from here to here. You're also going to see this question in that we're basically going to do the same thing we just did, only backwards. If you want to rewrite a sum over difference of logs as a single log, you're essentially using your expansion properties backwards. So powers are going to come back inside my logarithms. Sum's going to turn into a product inside a logarithm, etc. So if I look at this 1/2 log x plus 3 log x plus 1, okay, what's going to happen is this 1/2 is going to come in, this 3 is going to come in. So this is going to be log of x to the 1/2 plus log of x plus 1 to the third. Now, since these logs are added together, I can write it as a product. In that case, log of, I'm going to say square root of x, that's x to the 1/2, times x plus 1 to the third. And that would be my final answer. So writing it as a single log, we can consider this contracting logarithms. But really, this is just one thing to help you get more practice. But two, it's a way to simplify your answer. If your answer has multiple logarithms in it, it's better to write it with a single logarithm in the end. So let's try the next one. 1/3 log base 2 of x plus log base 2 of x plus 1. So I'm going to write this as 1/3 of log base 2 of x times x plus 1. And then that 1/3 is going to come in and I'll write it as log base 2 of the cube root, that's 1/3 power, x times x plus 1. And that would be my final answer. The key to this is if I'm going to bring these logs together or bring these logs together, they have to have the same base. Here, these are both base 10, these are both base 2. If I have a log base 3 of x plus a log base 2 of x, I cannot bring these together as a product because the bases aren't the same. When I expand, I keep the bases the same, so when I go backwards, the bases have to be the same. And that brings us to our last thing, which is something called the change of base formula. So earlier I referred to the log button on your calculator, and that log button on your calculator is just a base 10 logarithm. You also have a natural log button on your calculator. That's a base E button. But you don't have a button that looks like this, which basically means you can change the base. The reason is it's actually pretty easy to change the base of a logarithm. These formulas are the change of base formulas, which basically says this is how you can change the base of a logarithm to any base you want. The two that are probably the most important would be these two, base 10 and base E, because those are the ones that your calculator uses. But this one says I can use any base, B. So if I have a log base A of x, and I want to change that base A to base B, so one base to another base, I can do that. The new logarithm I'm going to be working with is going to be base B, but it's not going to just be one logarithm, it's two logarithms and they're divided. So this log is equal to log base B, which is the new base that I wanted to change to, which could be anything as long as it's positive, not equal to 1. I'm going to do log base B of x divided by log base B of A. Essentially, I change the base to whatever I want, and I take the log of the thing that I was taking the log of before in the numerator, and I take the log of my old base in the denominator. So let's erase some of this so you can see it better. So we have log base A of x equals log base B of x divided by log base B of A. Now that's fine, you can do that, but you're probably going to want to use one of these two instead. This is log base A of x, so you have some logarithm with some base, is equal to log base 10 of x over log base 10 of A. It's the same formula as here, but instead of just some random B base, I have base 10. This one, same deal again. Instead of some random base, it's base E, which is natural log. So natural log of x over natural log of A. So if I wanted to do something like this, find the log base 4 of 30. Back to where we started, we would have said 4 to what power equals 30? Well, that's not easy to do, right? 4 to the second power, 16. 4 to the third power is, what, 64? So this is 30. Well, it's neither of those, and it's not an easy one to find. This is where you want to use your calculator. So I'm going to rewrite this as log of 30 divided by log of 4. And these are base 10s. So I'm going to use my calculator. This is how I would plug it into my calculator. Log 30 divided by log 4 using the base 10 log button on my calculator. Or I can use the natural log button, log 30 over log 4 with natural logs. That would also work, and that'll give me the answer for log base 4 of 30. Now you'll never get the exact answer, so I should really do this. But you will get a better answer than just guessing. I mean, if you're going to guess on this one, you would say the answer is somewhere between 2 and 3, right? Because 4 to the second, 16. 4 to the third is 64. 30 is between 16 and 64. So, you know, you could say it's somewhere between 2 and 3. But if you put this in your calculator, you should get, let's see what I get. You get 2.45, 3, 4, 4, etc. And you get a better decimal than just saying something between 2 and 3. So this is the answer. Now it's never going to be exact because what happens is this is going to be a decimal that goes on forever and never repeats. But at least you can do pretty good in figuring out what the answer is. And this is how the change of base formula works. I can take any base I want and change it to any other base. The bases you're probably going to want to change to are base 10. And I take the log of this thing divided by the log of this thing. And that's how it works. And I could do natural logs too. You should get the exact same answer. So check this on your calculator and make sure you can come up with this particular answer.